Okay, we're going to go over exponential growth and decay, which maybe you've heard about before, and the main difference that you've probably seen is how exponential growth is when we have an exponential with a base that's greater than 1, and then exponential decay is when the base is between 0 and 1. But now we're going to have to write these equations for ourselves. For exponential growth, you'll see two types of problems. Sometimes it'll just tell you the value of b, and if it does that, then you have y equals a times b to the power of t. Or it'll give you a rate that this context is growing by. And if you're ever given the rate of growth, then you're going to do y equals a in parentheses 1 plus r to the t. Now, in both of these equations, y is the final amount, and a is the initial amount, t is time. And then r, that would be your rate, and b, that's just the base. So when we read a problem, we want to determine whether it's just giving us the base or it gives us a rate of increase, which would be a percent or a decimal. In this first example here, we have 900 strep bacteria are found on a doorknob. The number of bacteria doubles every hour. So right here, it tells me that it grows, it's doubling every hour. So I know that it's growth, but what this means is that base equals 2. This is giving me the exact value of the base, not a rate of increase. Even though they seem very similar, because it's that whole number, I know it's the base. So we want to write an exponential equation to represent this situation. So we've got y equals, now our initial amount was back here, that was 900. So y equals 900 times 2 to the power of t. And there's our growth for the strep bacteria. Part B says, how many bacteria will there be after 4 hours? So it is plugging in 4 for t. So we get y equals 900 times 2 to the 4th power. I'm just going to plug that in my calculator. So 900 times 2 to the power of 4, y equals 14,400 bacteria, which grows. But there we go. All right, now for decay, decay could also give you a base, but more often it's going to give you the rate of decrease. So in this one, we will usually use this formula, y equals a times 1 minus r to the t, where all the variables are the same as before, but we're just doing 1 minus instead of plus since it is decay. So in this example, caffeine is eliminated from the bloodstream at a rate of 15% per hour. This is our rate. You drink a soda and the caffeine in the bloodstream reaches its peak level of 30 milligrams. 30 milligrams, that's our initial value. Write an equation that represents the amount of caffeine remaining in the bloodstream after t hours. So that would be y equals 30 is the initial amount times 1 minus r, which is 0.15, raised to the t power. Now we're going to simplify this. So we get y equals 30 times 0.85 to the t. And if you think about it, if 15% is how much it's decreasing by every hour, then you're left. So if you're decreasing by 15%, then what you're left with is 85%, just in case you wanted some context for why we do 1 minus r. But if you don't need to know why, then there you go. There's the formula. All right, in B, use the equation to predict the amount of caffeine remaining in the bloodstream after 1 hour and 4 hours. So this is asking us to do this problem twice, once for t equals 1 and once for t equals 4. So we're going to start with the t equals 1. We've got y equals 30 times 0.85 to the first power. Plugging that in, I find that after 1 hour, you will have 25.5 milligrams of caffeine still in your system. Now, for 4 hours, we've got y equals 30 times 0.85 to the 4th power. Plugging this in, 30 times 0.85 to the 4th, and I get 15.66 milligrams of caffeine left in your bloodstream. All right, now in C, after how many hours will there be 10 milligrams left? So now this 10 is giving me a y value, and we're trying to solve for t. So we're going to plug in 10 equals 30 times 0.85 to the t power. And now we're going to solve. So step 1, I'm going to divide both sides by 30. And I get 1/3 equals 0.85 to the t. Now I need to get t out of the exponent, so this is where we're going to switch to log form. I'm going to have base 0.85 of 1/3 equals t. So log base 0.85 of 1/3 equals t. And now I just need to plug that into my calculator. And I get 6.7599 hours is how long it will take. And that's growth and decay.